Welcome back to my channel. In this video, I will show you how to use the three kinematic equations using a sample problem. I will also show you a technique to accurately represent the motion of the object in our sample problem. We will be using graphs such as the distance time graph, velocity time graph, and acceleration time graph. So let's begin doing our problem. The problem is taken from one of the textbooks, and the problem goes like this. An egg is thrown nearly vertically upward from a point near the cornice of a tall building. The egg just misses the cornice on the way down and passes a point 30 meters below its starting point, 5 seconds after it leaves the thrower's hand. Ignore air resistance. We need to find A. The initial speed of the egg, B. The maximum height that the egg would reach with respect to its starting point, letter C. What would be the magnitude of the velocity at the highest point, letter D. What would be the magnitude and direction of the acceleration at the highest point, and letter E. We need to provide the graph motion for the egg. So in this case, our representation would be given here at the bottom. So the egg was thrown nearly vertically upward and it almost misses the cornice. So we have our three kinematic equations. I would label them, this one as equation 1, equation 2, and equation 3. The next thing that we need to do is to write down all the given. So in this example, the object undergoes pre-fall. So when an object undergoes pre-fall, its acceleration remains constant all throughout the motion, and its value is equivalent to negative 9.8 meters per second squared. Another thing that is given in the problem is that it passes a point 30 meters below. So we could write it as delta y equivalent to negative 30 meters, and the time given of 5 seconds. And we could also say that at the top, or at the highest point, that the velocity at the top is 0. So let us now proceed with letter A. Let us now find out what would be the initial speed of our egg. Now within the given, which equation could be best used, or which equation is going to be the most appropriate to solve for our initial velocity? We could use these three, but it would give us different results. Okay, suppose we have, or suppose we use the first expression and we plug in all the given. So we have 0 equivalent to the unknown, which is the initial velocity, plus ayt. So in this case, the initial velocity would be equivalent to negative ayt, or that would give us negative 9.8 times negative 1, and a time frame of 5 seconds. So in this case, our initial speed would be 49 meters per second. Okay, now what if we use the second equation? If we use the second equation, we would have an expression like this. So we want to find out the initial velocity. So a little algebra would give us this expression. Okay, now if we plug in the values, we could see that this expression would give us a negative square root. Okay, which is negative 588. So we don't want that, right? Why is it that we don't want such answer? Because this would give us this would give us an answer which is known as a math error, or an answer which has no physical interpretation. Okay, so let's try the third expression. For the third expression, we have negative 30. I think it's better if I write it in an algebraic manner first. So we have delta y equivalent to v naught yt plus 1/2 ayt squared. So we want to solve for vy. So vy would have a working equation of negative delta y over t minus 1/2 ayt. If we plug in the values of all the given, we will have 30 meters divided by 5 seconds, okay, minus 1/2 negative 9.8 meters per second squared multiplied by 5 seconds. So here we will have negative 6 meters per second. Here we have a negative and a negative, so we will have positive. So that's going to be 9.8 times 5 divided by 2, which is 24.5. Okay, 24.5 meters per second. And we subtract 6, we take away 6, we now have 18.5 meters per second. So which of these three would be the most appropriate and would have or would give us a more realistic result? In this case, the one throwing the egg is a human, so a human can most likely be capable of throwing such object with this given velocity 18.5, because if an object has been thrown at these speeds, then it would mean that this human possesses a superhuman strength, because as you can see, the object would travel at a speed of 49 meters per second. That is roughly 100 kilometers per hour. Okay, so I would definitely choose the answer here as the initial velocity to be 18.5 meters per second. Okay, now we are asked for letter B. How high does it rise above the starting point? So how high? I will just illustrate it again. So let's say this is the rooftop, and this is the manner that it was thrown. Okay, so at this point we want to find out how high or what height was it able to attain. Okay, so again, the given from this problem is the acceleration. Okay, and at this point we already know the initial velocity of the egg, which is 18.5 meters per second, and we know that the speed at the top, okay, the speed at the top would be 0. Okay, so which equation can we use here? Can we use the first equation? Okay, definitely we cannot, because it doesn't have the parameter that we want to find out. So we are down with 2. Either we use the second equation or we use the third equation. Now if we want to use the third equation, we will be burdened to solve for the time that it reaches the maximum height. Okay, so if you don't want to be burdened to show or to solve for the time to reach the maximum height, then the most appropriate one would be the second equation. Okay, but nonetheless we will see if we use both of the equations. Let's try to see if we would arrive with the same answer. Okay, so in this case we will utilize the second equation. So I will just rewrite the second equation for reference. Okay, so if we want to solve for the maximum height, which we can find here at delta y. So we first solve delta y. So delta y would give us vfy squared minus v naught y squared all over 2ay. Okay, and you should also note that delta y is y minus y naught. Okay, so that would give us, for bfy, if we plug in its value, that would be 0. So that would be negative v naught y squared all over 2ay. And since we are starting, or we are considering that the starting point is at the rooftop, we can set y naught equal to 0. So therefore we have y equal to negative v naught y squared all over 2ay. If we plug in the values here, that would be negative 18.5 meters per second, and then squared all over 2 times negative 9.8 meters per second squared. So that would give us a value of, what is 18.5 squared? 342.25. But there's a negative sign outside, and then here we have 19.8 times 2, which is 19.6, and a negative value again. Okay, I forgot the unit, so this is meter squared per second squared, and this one is meter per second squared. Second squared cancels out, 1 meter here and another meter here cancels out. So if we divide 342.25 by 19.6, we would have an answer of the maximum height achieved to be 17.46 meters. So that's the maximum height that the object, or the egg, had obtained. Okay, so that is letter B. Now what's next? We are asked for the magnitude of the velocity at the highest point. So as we can see, the velocity, as it goes up, it slows down, and when it reaches the maximum height, the velocity actually becomes 0. Velocity at top is actually 0. Okay, how about letter D? What are the magnitude and direction of the acceleration at the highest point? So how can we do that? How can we determine the acceleration? Well, it's already given. Okay, so the acceleration, the magnitude of the acceleration is actually 9.8 meters per second squared, and its direction is actually downward. That's why we have a negative sign being used all throughout the problem. Okay, now we are down to the last one, which is letter E. Sketch the graphs for the motion of the egg. Okay, Now, in order for us to have an accurate representation of the graph, instead of estimating or doing rough estimation with our computation, we will be utilizing a program known as Microsoft Excel. Okay, so in this program, as being shown here, you have already pre-made a pre-made graph, but we will start from scratch so that you can follow through on how this thing is being done. So the parameters that we need to find first are the parameters for the distance time graph. So in this case, that's t for the time, and the distance is y for the height. So in this case, we will choose a variation or difference of 1, and what else? The initial velocity. Okay, the initial velocity is actually 18.5 meters per second. Okay, so to get the height, we are going to use, what are we going to use? In this part here, wait, let me fix my pen. Okay, so in this part here for y, the formula that we will be using is v naught t plus 1/2, sorry, this is on along y component, v naught yt plus ay, sorry, v naught yt plus 1/2 ayt. So we are missing a value for the acceleration, which is negative 9.8 meters. Okay, so to set that up, we just follow the formula. Okay, so this, we anchor this one multiplied by the time plus 1/2, we anchor it again with the acceleration times t squared. Okay, so just click OK and drag it down. Alright, so if we want to have a graph, we just highlight this one, click insert, and recommend the chart, and choose the scatter graph, and there you have it. We now have a graph for the distance and time. Now what about the graph for the velocity time graph? Now for the velocity, for the final velocity, that is, we will be using the first expression. So in this case, that would be equivalent to the initial velocity, we anchor that one, plus the product of the acceleration and time, and we drag. Okay, so to get the velocity time graph highlight it again and recommend the chart, and again we choose the scatter graph. Okay, so there you have it. We now have two. Now for the acceleration, well, obviously the acceleration remains constant all throughout, so we will have a graph which is just a constant. Okay, now to give it a more appropriate look, the graph would be looking like this. Okay, so that is quite neat, accurate, and properly labeled. Okay, don't forget to properly label the axis of your graph, and to properly label the units. So in this graph I forgot to label the axis that I have used, so I should have written here for the distance, I should have written here meters, and for the time it should be seconds. For acceleration, they should be meters per second squared. For velocity, that's meters per second. Okay, and again for time, that is in seconds. Okay, so let's not forget to do the proper labeling and the proper name of the graph. Okay, so I hope you have learned something new from this video, and see you next time.